Now we are leaving the world of smooth S-curve, and now we are entering this reciprocal function. And these are very different functions from what we see earlier. Look at this function y equal to 3 over x. Notice something immediately that is different from another graph. There's no value where x equal to 0. This is because we cannot divide anything by 0, which means that this graph has a gap in the middle. Let's go to the table and see what's happening. When x equal to 1, we get y equal to 3 over 1 equal to 3. When x equal to 2, we get y equal to 3 over 2, which is 1.5. So x gets larger, y gets smaller. You see when x equal to 3, y equal to 1. This is different behavior from the cubic function. And also take a look at the negative side. When x equal to negative 1, we get y equal to negative 3. The graph somehow jumped to the opposite quadrant entirely. When you look at the actual graph, they're kind of like two separate curves that never touch. They approach but actually never reach the x and y axis. These invisible boundary lines are called asymptotes. The graph get infinitely close but never crosses them. Notice how different this is from the cubic function. Instead of having one continuous S-curve, we have two separate pieces, kind of like two separate pieces of graph living in opposite corners of the coordinate plane. As x approaches 0 from the right, y shoot up towards and then towards infinity. As x approaches 0 from the left, y plunges towards negative infinity. This behavior model kind of the real-world phenomena like electrical resistance or the relationship between speed and travel time. If you're driving a fixed distance, if you double your speed, you kind of half your travel time. We call this a reciprocal behavior. Now, if we look at y equal to 6x, it's different from y equal to 3 over x. Notice that the shape remains the same. We still have two separate branches in opposite quadrant that don't touch x equal to 0, meaning the asymptotes are still the same. But the coefficient kind of act as a scooting factor. Think of it this way, y equal to 3x model a relationship, but y equal to 6 over x model a relationship that is twice as intense. So they have the same pattern, but the magnitude is different. Both curves have the exact shape, but y equal to 6x is further from the axis. The larger coefficient pushes the branches away from the center, making the curve look more dramatic. To summarize, the coefficient matters. When a more than 0, both branches of the reciprocal function live in what we call the positive quadrant, the upper right and the lower left. This positioning never changes for positive coefficient. However, when the coefficient increases, the graph moves further away from the origin. Think of the coefficient as a push factor. A larger positive coefficient pushes both branches outwards, away from the center point. Conversely, when the coefficient decreases, the graph moves closer to the origin. A smaller positive coefficient will pull both branches inward towards the center. Now what happens when the coefficient becomes negative? We examine y equal to negative 3 over x and look at how it compares to our positive coefficient function. If you look at the table, the negative coefficient kind of reverse all our y value. You notice on the graph that the negative coefficient relocated the branches. Instead of the curve being in the upper right and lower left coefficient, the branches have moved to the upper left and lower right. This is what happened. When a more than 0, the branches occupy the opposite corner diagonally. And a less than 0, the branches occupy the other pair of opposite corners diagonally. So the negative coefficient kind of cause a reflection across one of the axes, flipping the entire graph into a different quadrant. We still have the same hyperbolic shape, the same asymptotes at x equal to 0 and y equal to 0, and the same behavior as we approach this boundary. And again, If we are drawing y equal to negative 6 over x, with larger coefficient, the larger of the absolute value, it pushes the branches away from the origin. So the coefficient negative 6 creates more dramatic curve than negative 3, but they're still the same quadrant, upper left and lower right. To summarize, if x equal to more than 0, you have the branches on the lower bottom left quadrant and upper right quadrant. And if x less than 0, you have the curve on the upper left quadrant and in the lower right quadrant. Second, asymptotes define the boundary. Every reciprocal function has two invisible walls, the vertical line x equal to 0 and the horizontal line y equal to 0. The function is undefined at x equal to 0 because we cannot divide by 0. And it approaches, but never reaches y equal to 0 as x get very large or very small. Thirdly, the coefficient a controls the steepness. Here is where many students get confused. The larger absolute value of a creates steeper curve that hug closer to the axis, while the smaller absolute value creates more gentle curve that sit away from the axis. Lastly, let's look at the domain and range. Unlike linear or cubic function, reciprocal function has some forbidden area. The domain excludes out x equal to 0, and the range also excludes y equal to 0. Lastly, there's a symmetry property. Both the branches mirror each other perfectly across the origin point 0 and 0. If you rotate the entire graph in 180 degrees around the origin, it will look exactly the same. Now let's move from y equal to a over x to y equal to a over x squared. This square denominator creates completely different behavior. The first thing that you might notice is that there's a symmetry. Unlike y equal to a over x, which have branches in opposite quadrant, both the branches of y equal to a over x squared live entirely above the x-axis when a more than 0. This creates a U-shaped pattern that is symmetrical about the y-axis. Then you can compare 3 over x squared with 30 over x squared. Both functions create the same basic shape, what we call a hyperbola with a vertical axis. But notice how the coefficient affect the steepness. The function 30 over x squared creates a somewhat more dramatic curve that shoots upwards as we approach x equal to 0. And here is what revolutionary about x squared denominator. It always produces positive value regardless of whether x is positive or negative. Since negative 2 squared equal to 4 and 2 squared equal to 4, both sides of our function behave identically. The asymptote still remain the same. We cannot touch x equal to 0, and the function approaches y equal to 0 as x gets very large. But now we only have one horizontal asymptote at y equal to 0, and the function always stays positive when a is more than 0. This kind of reciprocal function model different kind of real-world phenomena. Things like the intensity of light decreasing with the square of the distance, or gravitational force relationship. The square relationship creates more rapid changes and different behavioral patterns than simple reciprocal function. And what happens if we introduce negative coefficient to our x squared reciprocal function? Look at this graph. They are complete mirror image of the positive coefficient function. Instead of U-shaped curve opening outwards, now we have upside down U-shape that opens downward. Both this graph live entirely below the x-axis. The negative coefficient has flipped everything vertically. When we use a function approaching positive infinity as x equal to 0, we now have function going towards negative infinity. The symmetry about the y-axis remains perfect. The square denominator to ensure that both sides behave identically. Notice that the coefficient magnitude still controls the steepness. The function negative 30 over x squared has more dramatic downward curve than with negative 3 over x squared. Just as we saw earlier with positive versions, the largest absolute value pushes the function further away from the x-axis. The asymptote remains the same. X equal to 0 is still our vertical asymptote, where the function is undefined, and y equal to 0 is still our horizontal asymptote, that the function approaches but never reaches. This behavior model real-world situation with inverse square relationship that have negative effects. Kind of modeling how a debt grows with the inverse square of payment frequency, or how certain negative forces decrease with the square of the distance. The key insight is that the negative coefficient create a downward curve that mirror their positive counterparts across the x-axis. So what can we observe from y equal to a over x squared? To get a more than 0 and when a less than 0. Here's a quick recap. The fundamental shape is always U-shape or inverted U-shape with perfect symmetry about the y-axis. The symmetry comes from the x squared denominator. Whether x is positive or negative, x squared is always positive. The coefficient a helps to determine whether the graph open outward or downwards, and the absolute value control how steep the curve are. The larger value create a steeper curve that hug closer to the y-axis. Asymptotic behavior follow predictable patterns. We always have a vertical asymptote at x equal to 0 where the function is undefined, and the horizontal asymptote at y equal to 0. As x approaches 0, the function shoot towards infinity or positive infinity depending on the sign of a. For the domain and range, they are also very specific. The domain excludes only x equal to 0, but the range is limited to either all positive value or all negative value, never both. Also notice that the function never crosses 0 and never crosses the x-axis.
Smash your maths exams. Download Learn Maths Today for real exam questions and achieve top marks.